Yeah, so that you can easily immobilize this kind of nanomaterial, because they are also I mean they are also hydrophilic material, and carboxylic acid amine group, so they can easily adsorb on the hydroxyl group surface. They can easily react on the hydroxyl group surface. I mean that surface should be hydrophilic surface, so that the reaction will be much faster.
Okay, sir.
Clear?
Okay, sir. Clear.
Good, good. So any other questions,
Sir,
students? Tell me.
sir, can you start the recording, sir?
Uh, oh, recording is stopped. You also have right. You can also start recording if you
Okay,
want.
sir. Okay, sir.
Do you know how to start recording?
Yes, sir. Yes, we know, sir.
Yeah, please start the recording. You also
Okay, sir.
can. Hmm?
Hello.
Hello.
Sir, this part was in the last class. You just leave this part, biomineralization part. Please repeat this one.
Bioimmobilization part, right?
So this chloroauric acid part
Ah,
and all those things, application of negative potential. This part was not done
not clear.
clearly.
Yeah, that time, some visitor came in my office, so that's why. Okay, good. So yeah, let's start from here. So So I think all of you are here, right? How many? Only 35 students here today. Anyway, so as I'm saying, so please be on time, because I am actually following this class schedule very strictly, and I mean within time I will start the class. Okay, let's start. See, evident biotin, this immobilization that I taught you, this is kind of that I say this affinity binding. And another factor that I'm going to teach you, that is the electrodeposition. So you need this kind of method for immobilizing your biological stuff or some nanoparticle, or how you will fabricate your biosensor. See, so electrodeposition, this technique is nothing but this is kind of some negative potential when you are applying on your surface. Which surface? Your transducer or your electrode surface. Okay. So what you will do? Okay, I will show you a picture here. So like this. So this is your transducer. And on this transducer, so something like you have to make some barrier on the transducer so that solution should not spread out of this region. So how will make the barrier? So maybe you have to make some Teflon cell, or you have to you can take some plastic, uh, you make some hole, then you can put this hole on the sensor surface so that you can drop only the solution in this your working region area, and it will not spread other side, something like this. So so in this area, so you can drop some solution, something like chloroauric acid. So chloroauric acid HAUCl4, this is for gold nanoparticle formation, and H2PtCl6, that is called chloroplatinic acid, this is for platinum nanoparticle formation. So this is the two example I am saying here, but similar kind of salt for other metal nanoparticle also you can use. So let's show you these two example first. So for gold nanoparticle formation, something like you just use like 0.5 millimolar, something like some, suppose one concentration of chloroauric acid. I mean HAU, sorry, HAUCl4. So this is your chloroauric acid solution. Now you have to connect this working electrode with some potentiostat. Some potentiostat. So potentiostat, what is potentiostat? This is one kind of the instrument where you can apply, by using this instrument, you can apply some potential, something like suppose 0.3 volt. So negative, you need, if you need negative potential, you can apply some negative 0.3 volt, some potential you can apply, and you will get the when you can when you are applying some potential, maybe you will go, it will show some output, like something like in this area, if you apply like x-axis volt, y-axis maybe current. So if you apply some negative potential around minus 0.3, so in this area you will get some current like this. So you will get some output. Anyway, but we are not measuring any output in this case. Just we will apply some potential on the negative potential. Actually, see HAuCl4 in this case, gold actually +3 state. So +3 means its oxidation is the +3. So when you apply negative, then it will capture the electron. It will capture electron and it will go to AU0 state. So it is the nanoparticle. So this nanoparticle now will adsorb on the surface like this way. So then you will get a nanoparticle coated transducer. So your transducer will be gold nanoparticle coated when you will apply some negative potential on the this salt. Similar way for platinum nanoparticle. So you have to take some H2PtCl6, something like this solution, and apply some negative potential. So which potential you need? That also you have to optimize. I mean, if you apply like minus 0.3 volt, you will get some nanoparticle. If you apply like 0.1 volt, also you will get some nanoparticle. But different potential, you will their size, their surface, everything will be different. So that you have to optimize. So which one you need and which potential actually you are getting the better nanoparticle, and this and which potential you are getting highly active nanoparticle, that you have to optimize. That method you have to apply before fabrication your biosensor surface. Okay, so that part for electrodeposition. So let's now I will show you how we will use this electrodeposited nanoparticle for biosensor formation. See, so this is your transducer. Now after electrodeposition, your surface will have some nanoparticle like gold or platinum. Now, one thing I will tell you now. Antibody.
Sir,
Tell me. Yeah. Hello.
yes, sir. Sorry to interrupt, sir. I was just asking that can we use chemical vapor deposition also, like for the deposition of gold nanoparticles? Like,
See, the vapor deposition also you can use definitely, but you know vapor deposition a little bit complicated. You need the special setup. Huh? You know, right? Some special setup and very expensive setup also you need. And so for the and this system, electrodeposition system, is very simple. In the I mean, just in your lab or in your room, you can carry out very simple setup, very small setup. Just for potentiostat. Like, actually, right now we have very portable, like smartphone potentiostat we have. So we can apply with this potentiostat on your surface some potential on a cell. This is the electrochemical cell. So here you will be working electrode, your biosensor surface. Just drop the solution, apply some potential, and wash it. You will get the surface nanoparticle. Within a second you will get. Sometimes you can apply for point some 5 seconds, and immediately you will get many nanoparticle on the surface. So it is very efficient than vapor deposition also. That's I'm saying.
okay, sir, got it.
Got it? Okay. Now see, one thing I will tell you. As I said, that antibody, it has so many primary amine group, right? They have some pre-amine group. Now, if in a beaker, the small beaker, if you take some antibody solution, so you take some antibody solution. Now, if you add some gold nanoparticle solution, gold nanoparticles. So how you will get the gold nanoparticle solution? That also means I just now I taught how you will get gold nanoparticle on the surface. But sometimes you need gold nanoparticle solution. I mean, that is on the surface. You cannot detach it, right? If you scratch it, something they will be detached, but also they will damage. Surface will be damaged. So, but sometimes we need nanoparticle in the solution. That also I will teach you. How you will get the nanoparticle in the solution? See, first step. So that you can make in a tube. You just take HAuCl4 chlorhydric acid solution. Right? Some concentration you have to take like 0.5 millimolar. Then add here some reducing agent. So reducing agent like sodium borohydride, NaBH4 is a reducing agent. This is kind of reducing agent. Also sodium citrate. They're the reducing agent. Sodium citrate also kind of capping agent also. They are helping to stabilize the nanoparticle in the solution. So you can add both also together in the solution. So they will help to reduce gold nanoparticle from HuCl4 to nanoparticle Au0. So they will be in the solution. So one red color solution you will get that contain gold nanoparticles. Clear? So it's a very simple process. So as from my experience, I know. So if you add the sodium borohydride in the chloroauric acid solution, so within a few seconds, your solution at first your solution will be very something like yellow color, or sometimes it is not much in the deep color. But when you add the sodium borohydride, immediately you will get some reddish solution contain gold nanoparticle in this tube. So like this way, you will get gold nanoparticle solution. Similar way, platinum case also. If you get the H2PtCl6 solution in a tube and add the sodium borohydride in the tube, you will get platinum nanoparticle in the solution. Clear, guys?
Yes, sir.
Sir, I have one confusion.
Tell me.
Sir, initially we were doing this electrodeposition thing, and then we are just putting chloroauric acid in the solution. I didn't get what these two things are.
Oh, see, I just already mentioned. So electrodeposition case, you are getting nanoparticle on the surface that will be attached because of electrical force. It will be attached on the surface. When you are applying some potential, it will be attached. They will not be detached easily. So when you watch the surface, so you will see your transducer that contain nanoparticle. Okay, that is on the solid surface. And second one that I am telling you, that is in the solution, means in a beaker or in a test tube, you can take some solution of chloroauric acid. Now if you apply some solutions of the reducing agent like sodium borohydride, you will get nanoparticle in the solution. That is in the solution. And here nanoparticle.
Why these two things are doing separately? We are doing.
Yeah, see, the first thing that I mentioned, that is for your surface modification. Okay.
Yes,
Okay.
sir.
Second thing, you can see that I am going to teach you. Second thing, how you can use this gold nanoparticle. As I said, in a beaker, you can take some secondary antibody. That, as I said, the antibody already contain amine group. Okay, so this is antibody solution in a beaker. Now you can add on this beaker a gold nanoparticle solution that you synthesize by this reducing method. Now clear? So
Yes,
this,
sir. Yes.
this nanoparticle, now you can add on this secondary antibody. So this solution that contain the gold nanoparticle, they can bind with this amine group. Actually, gold nanoparticle, they have, this is very natural phenomena. They has very strong affinity to the amine surface. So if any protein they have that has the amine group, so it will easily they can bind. This is kind of non-specific binding, not the specifically like that I said, like EDC and HS, they are very specific, right? So they can only attack the carboxylic acid, something like this. In this case, if you have the amine group on the primary amine surface, so many gold nanoparticle can bind on this amine surface. So no need any extra reagent. Just you have to incubate. So in a beaker, you have to take just secondary antibody, and you can add some gold nanoparticle solution. You can shake them well properly for 5 minutes or 10 minutes. Then you will get some secondary antibody that conjugated with gold nanoparticles. So how you can separate them? Because there's so many unbound gold nanoparticle also there. So you can centrifuge them. Centrifuge means you can take this solution in a centrifuge tube that contain gold nanoparticle, also some free nanoparticle also there. Now if you can centrifuge, means you have to spin it around 12,000 rpm. If you spin it, then this all the this antibody that is conjugated with gold nanoparticle, they will be separated from the solution. Actually, there is some spin you have to optimize. Which spin? Maybe some spin, maybe all will be separated together. Nanoparticle and antibody both. So you have to optimize which spin is better for separation of only secondary antibody that conjugated with gold. That we can separate by centrifuged tube, by centrifuge method. In the centrifuge instrument. Okay. Clear? So how we can conjugate a secondary antibody with gold nanoparticle? This is very simple, just addition.
Sir,
Yeah,
uh,
tell me.
sir, like we previously studied that we need gold nanoparticles to so that that an NP will get reduced to AP, kind of
Hmm.
to produce those electrons. So like if gold nanoparticles are already present, so they and they will bind with the secondary antibodies,
Yeah.
so they do not need PSA to be present there for the production of for the
No.
reduction of NP to AP.
Yeah, this is something depends. See, your secondary antibody, yeah. So secondary antibody conjugated with gold, right? And you separated this. Okay, you
Yes.
separated, and that is in a tube. So in a tube, you have some secondary antibody that is conjugated with gold nanoparticle. So what you are doing? So that is your primary antibody coated biosensor, right? This is your biosensor for PSA detection, right? So when you add the target of the PSA on the surface and washing, then there is no secondary antibody, just primary antibody and PSA there, right? Now on this surface you are adding this secondary antibody conjugated gold nanoparticle coated solution, right? So when you add the here and wash the surface, then only your secondary antibody that is conjugated with gold will come on the surface. Otherwise it will not be there because antigen there, that's why secondary antibody will be there, and your secondary antibody conjugated with gold, so naturally it will be there.
Yes, sir. Yes, sir. Got it. If there is no, sir, those antigens, so
No,
if we wash that, so these secondary antibodies will get
no,
washed away.
they will
Yes.
be washed away. Right, they will be washed away. Clear?
Sir, then what
Yes,
is
sir.
the purpose of our electrodeposition of that gold on the earlier one?
Okay, okay, that I will come. Okay, so that's I not completed yet because he is asking another question that I came to that part. But that is good. You just keep asking the questions because everything will be clear like this way. We are not going like point by point. But if anything not clear, I will clarify immediately. Okay, so now we conjugated like this way. So then in the electrodeposition, so why we are making this nanoparticle on the surface, right? So our surface now gold nanoparticle coated. So one thing, see, sometime we are making some glass surface for our transduction. Suppose, suppose, wait. So this is your glass surface, okay? So glass or plastic, so or a flexible plastic. But how you can make it conductive, right? So you have to make the surface conductive. Otherwise, the electron will not transfer. So for that, you can deposit the gold nanoparticle. That is one thing. So because you can, so only gold plate is highly expensive, but if you can make like glass surface, then if you coat the gold nanoparticle, then it will be cheaper. Got it? One point.
Yes,
Uh,
sir.
that is
Sir,
one point.
sir, in this context, I have just simple silly question. Sir,
Hmm.
instead of doing all this electrodeposition, can't we directly take a surface which is conducting in nature directly instead of taking glass plate and coating it with gold and all those stuff process?
No, yeah, that you can take, but sometimes we have lots of some side effect there. Like you just take a like something like you can take some platinum electrode itself. It is very highly conductive. Just don't think about the price right now. Just platinum
Yes.
electrode. You can, so it is highly conductive. It is metal surface. No need the electrode deposition, right? But
Yes.
thing is that on the whole this surface, some you can say some interfering species, they will show high activity. So you will get high noise, I mean background current. So because to avoid this background current, we are not using the whole like this plate. We are using nanoparticle coated surface. And another thing, so this way you can remove, you can minimize the background. Another thing, on that surface actually, uh, you can minimize the cost also. Now think about the cost, because you can use the glass, then you can coat this one. And then the third point is this. So your surface now coat with the gold nanoparticles, right? Now, as I mentioned, it has the very high affinity with the amine group. Then you can easily immobilize the antibody on the surface. You can easily immobilize antibody on the surface, right?
Yes.
So this electrodeposition is basically help you like this way, the immobilization of primary antibody on the surface. Clear, guys?
Yes, sir. Yes, sir. Clear now.
See, just I am just guiding you some. So this is not like the textbook. See, how I am teaching you. This is not like some textbook theory I am teaching. I'm just giving so many information, right? Some technical information I am giving you. So just catch it. Try to catch it and use. Try to apply it when you are fabricating something device. So many technique I am telling you every day. So try to gather all the information and use anywhere. I mean, in the exam actually I will ask you some question like this. So design a biosensor surface for detection of cancer biomarker like PSA. So that only I will ask you. So then any design you can apply for the biosensor device development, right? So this kind of question I will give during the exam. Okay. So this is one technique. Yeah. So that's all for the electrodeposition of gold and platinum. Now come to the next topic. So guys, so it is clear, right? Until here, it is everything clear, all of you?
Yes,
There is
sir.
so many students from other background. I am not getting any question
Yes,
from
sir.
you. Divyangshu, what about you? Divyangshu, Divyangshu Gupta. Is it clear for you?
Yes, sir.
Clear, right?
Yes,
Okay.
sir.
See, now I am coming the next topic, that is the electrochemical biosensor. So as I said, this class actually we are interested on the very much specific biosensor, that is electrochemical biosensor. So why that I already taught you that it is very simple, easily we can miniaturize and cost effective, right? We don't no need to depend on the highly expensive and bulk big instrument. That's why. So what is the electrochemical biosensor? So electrochemical biosensor is a class of the biosensor where we functionalize the different kind of biomolecules on the transducer surface. Then we can detect them by the help of electrical signal like current or like charge, something like this. So we'll apply some potential. So this is the input. So input will apply some potential and output will get some current or charge. So by the help of amount of current or amount of charge, we can say how much target present in the solution. I mean the concentration of the biomarker you can say. So you already know, right? What is the biomarker and what is the target. So biomarker means so that you are going to detect. That is your target. That is your biomarker that you are going to detect, right? See, so electrochemical transducer is this one where you are immobilizing your all nanoparticles, your biological stuff, everything, where you're immobilizing and your chemical signal transferring to the electrical signal. So where your, I mean the signal transfer and also amplifies. So sometimes we need to amplify the signal because you are getting some signal, but that signal is not enough to detect. We have to amplify them chemically or some applying some nanomaterial on the surface. So we have to amplify them. So how we can amplify that I will teach you maybe next class. Okay, so this is the electrochemical biosensor. there is so many technique, electrochemical technique. How, I mean, as I said, this is the output. Output will be current or charge, something like this, right? So when you apply some potential. So based on this, we put some nomenclature like cyclic voltammetry. So this is kind of the electrochemical technique, so that we can detect our target. Chronoamperometry. This is kind of technique. Chronocoulometry, electrochemical impedance spectroscopy. So this four is a very important and very basic for electrochemical biosensor. So this four technique basically will help you to detect your biomarker concentration in the sample. Okay, so now I will teach you this all the technique. So what is the definition of this technique and how they look like. Yeah. So these things I will teach you now. So before going the different technique, so at first I will show you our electrochemical cell. So here the cell means not the biological cell. So here we are saying the electrochemical cell or electrochemical system, electrochemical cell or electrochemical system. So this is the cell, this one. So this is cell. This is electrochemical cell, electrochemical cell. So what is this? So electrochemical cell will contain 3 electrode system. So generally, like the battery or other cases, there is 2 electrode already present. Right? One is cathode and another is the anode. Right? So cathode and anode concept you already know in your 10+2 level also you know already. Cathode one and another is the anode. Right? So generally in this 2 electrode system, this electrode potential, so it contains some potential. Anode also it has some potential. So this potential is not fixed. They are variable. They are changing always. But in the 3 electrode system, as I am saying, in the electrochemical cell, we will apply a fixed potential. Right? So that's why we should have a reference electrode. We should have a reference electrode. By the help of that reference electrode, we can measure how much fixed potential we are applying on your working electrode. Okay, let's come the definition of the what is the working electrode, what is the reference electrode. See, suppose, yeah, this black one, this one, this is the one. So let's remove this one. Yeah. See, so this is the working electrode. So working electrode, this one. So this is number 1, working. And this one, this is the reference electrode, number 2. Another electrode, number 3 is the counter electrode, this one. So 3 electrode means one is working electrode, one is reference electrode, and the counter electrode. So what is working electrode? Working electrode means where you are immobilizing your biological stuff like antibodies, you are detecting the antigen. So that is the working electrode. So you are working on that, right? So your actual biosensor is fabricated on the working electrode surface. Huh? So your working electrode surface, your biosensor fabricated. So it can be made by, like as I said, like glassy carbon, gold, platinum, or you can immobilize on the surface gold nanoparticle by electrodeposition, something like this. So you can work on this. Reference electrode, this electrode potential fixed, will be fixed, constant, right? So reference electrode means by the help, when we are comparing how much potential you are applying on the working electrode, that will decide the reference electrode. So with respect to reference electrode, you are applying, like if you are applying 0.3 volt, it means with respect to this reference electrode, you are applying 0.3 volt. So your reference electrode potential should be fixed during your whole experiment. If reference electrode is not good, I mean, which material you should choose for the reference electrode? That is the one question, right? Because sometimes the potential of the reference electrode can be changed time to time. Then that is not good material for the reference electrode, because in the potentiostat, here actually you fixed, like you are applying 0.3 volt. So I mean all the program, everything done. Although you are applying 0.3, but reference electrode potential if change time to time, then actually not 0.3 volt is not applying on your working electrode, because reference electrode potential is changing. That's why for a better biosensor, for a very good biosensor, your reference electrode potential should be constant always. So I will now let you know which reference electrode is better.
करे हो
Which,
क्या?
hello.
नहीं कुछ स्मेल आ रहा है इसलिए.
So please mute guys who are talking, and if you not participate the discussion, please mute. Okay, so this is the definition of the reference electrode. A counter electrode. Counter electrode actually will help you to get all the output signal. I mean, see, so you are applying some potential with respect to reference electrode, then you are getting the output like current, right? So electron is flowing right from your working electrode to counter electrode. So by the help of counter electrode, actually you will get like current or charge, whatever, that can be measured by the help of counter electrode. So basically your current is flowing through counter electrode. Okay, so that's why your counter electrode material should be highly conductive, very highly conductive, like platinum. Generally we are using platinum as a counter electrode because it is highly conductive. Its resistance is very low. Okay, so in the 3 electrode system, that's why we have 3 electrode. One is working, one is reference, and another is counter. So on the working, we are immobilizing all the biological stuff. We are fabricating our biosensor. So actually we are detecting on the working electrode surface. Reference electrode, its potential or its potential, I mean, it is constant. So with respect to reference electrode, we are applying certain potential on the working electrode. And what is counter electrode? Counter electrode is helping you to measure the current or charge, whatever you are measuring. So actually current or electron, everything flowing from working electrode to counter electrode. That actually you are getting the output. So that's why your counter electrode material should be highly conductive or resistance should be very low. So that's why we are using platinum generally as a counter electrode. And which material we are using the reference electrode? Generally, reference electrode means silver chloride. This material, silver chloride, or we are using hydrogen electrode for the reference electrode. So I will teach you now what is the AgAgCl, what is hydrogen electrode. So hydrogen electrode case, we are considering its potential 0. So if you are applying 0.3 volt, it means with respect to hydrogen electrode, you are applying 0.3 because it is 0. And silver chloride case, actually it has its own potential around like 0.1 volt. It has its own potential. So if you are applying like 0.3 volt with respect to silver chloride, but compared to hydrogen electrode, actually you are applying how much? 0. How much? Actually you are applying. So it is actually 0.1 volt. Compared to that, you are applying 0.3. So it is actually 0.4 volt. You are applying, right? Compared to hydrogen electrode. So hydrogen electrode, its potential very constant. It is not changing. So what is the definition of hydrogen electrode? I'll teach you next slide. And AgAgCl kind of the AgAgCl means this is kind of silver rod. On the silver rod, there is some silver chloride salt. Silver chloride, you can coat the silver chloride. We can coat the silver chloride on the surface of the silver. So its potential actually very constant. It is not changing with time. That's why we are using this one as a reference electrode. Guys, dear students, it is clear now?
Yes, sir.
So it is very basic.
Yes, sir.
It is very basic thing. Let's go to the next one. That, as I said, anode and cathode. So I will give you some very brief idea what is anode and what is cathode. See, anode means where oxidation occurs. Oxidation. Cathode means where reduction occur. Hmm. What is the oxidation? If one like iron Fe, suppose Fe means iron. So FeCl3 means iron chloride, right? So here iron oxidation state is +3, right, guys? Fe +3 right, oxidation state. You know this one, right? Oxidation state in the 10+2 level you learn already. So, so if Fe3 plus, if it capture the 3 electron, then it will go to Fe0, right? So it means it is taking electron, it means reduction happen. It is reduced. It is reduced, and this phenomena is called reduction, right? This phenomena is called reduction. So, and oxidation, what is the oxidation? Back process is the oxidation. If Fe0 convert to Fe3 plus, so generally cation or anion, when they are in the solution, they are in the cation stage or anion stage. But if they are in the solid state, in the salt, then it is like FeCl3 in this stage, like this, right? So if we convert Fe0 to Fe3, means 3 electron will be released. So this phenomenon is called the oxidation. When electron release, it is called the oxidation process. So Fe0 is oxidized. So it is oxidized and it form Fe3 plus. Clear? This is very simple, right? You already learned this one in 10+2 level, your HS level. So in the anode, actually oxidation happen. So oxidation happen means so electron will be released. So there is so many electron on the anode surface. That's why it is negative charge. In the cathode, actually reduction happen. So reduction means in the cathode reduction happen. Reduction means they will capture the electron. That's why cathode surface is the positive charge. So where reduction happen, that is positively charged. Where oxidation happen, that is negatively charged. Right. So now, what is the anodic current? So I will show you some few terms that is necessary for the electrochemical measurement. What is anodic current? So during the oxidation, what we measure the current, that is the anodic current. Generally, anodic current goes to minus to plus potential range. So if this axis is the potential, if this axis is the potential, and if you want to scan, and if you want to get the, if you want to scan anodics, if you want to get anodic scan, or if you want to get the anodic current, then you have to scan your solution from negative to positive potential, and opposite one will be the cathodic scan. You will get the cathodic current. See, now the another terminology that need for all the technique, that is the electrode potential. All the electrode. So when in a solution you dip that I mentioned, that some electrode like as I mentioned, some like copper electrode or zinc electrode, then it will have some certain potential. So you can see here, like if it become the cathode means, as I said, so in this case, here reduction happen, right? So reductions means it will, so in a suppose you have a copper sulfate solution. So on the copper surface, reduction will happen. Reduction means copper 2 plus will get 2 electron, and then it will form copper. So this one become positively charged. That's why. So like this way. So it is the cathode, it is the anode. Zinc in case it is oxidation will happen. So it will be the negatively charged, and it is the anode. And what will be the actual E cell? E cell means what is the potential of the total cell? That is the E cathode minus E anode. That is the total potential of your cell. So if you measure the potential of the cathode minus potential of the anode, is your E cell, potential of the cell. So your electrochemical cell potential will be this one, cathode minus anode. See, now in the 3 electrode system, you will have only one working electrode, right? So like gold, and you will have one reference electrode. Like suppose you have here you can see this is the hydrogen electrode. So hydrogen electrode, it is like this. So on a glass tube, you have to pass the hydrogen gas. Uh, so in the solution, there will be actually platinum on platinum surface. So actually hydrogen electrode case, it is the something like this reaction will happen. So we consider its potential 0. So with the respect of the hydrogen electrode, now we can measure how much potential you are getting for the gold electrode. That is your working electrode. So this is just for information. So I'm not teaching more here. So let's skip these few slides. And yeah, tell me if you do not understand. If you're not clear, please tell me. I can give you information.
Sir, the last one was a 2 electrode system, and previously we discussed 3 electrode. So like in both the if we use hydrogen electrodes in the 2 electrode system, we can easily measure the correct potential.
Yeah, that's the thing. Means in the 2 electrode system, actually that like this way we are measuring the standard potential. That is called standard potential. So I mean your hydrogen electrode is fixed, right? This is the 0 potential, and suppose I provided you one unknown electrode that you don't know, some metal rod. So you can easily measure how much potential this one. Now if you can use this one in your 3 electrode system, now you know that is your potential of your like suppose it is a platinum metal. So if its potential is very constant time to time, then you can use this one as a reference electrode in other case in a 3 electrode system. So like this way, actually we are comparing other potential with the hydrogen electrode.
Okay, sir.
Okay, so that's actually standard potential. That terminology actually I'm going to teach you that this kind of terminology will come when I will teach you the electrochemical biosensor. So another terminology will come, the formal potential. So formal potential means see formal potential. I will tell you. This is see just I will show you one equation. This is called the Nast equation. I think you already know the E electrode. E electrode means in the 3 electrode system. In the 3 electrode system, 3 electrode, one is working, counter, reference. So E electrode means we are saying E0 minus RT by NF ln activity of the R means this is the product part and this is the reactant part, right? So this is the activity of the product part by activity of the reactant part. So this is the Nast equation. So I'm not going to go the derivation part. So just I'm showing this one. So see this E0 is called actually the formal potential. So means actually see. So as I said, the E cell means the cathode minus anode, right? This is the actual total potential in case of the cell. And E electrode, I mean, so this is the actual the potential. I mean, this is the working electrode potential. You can calculate it by the help of this equation. So A means the activity. So activity of the product and activity of the reactant. So generally, activity we are considering some constant into concentration. So it is proportional to the concentrations of your reagent. Suppose Fe3 plus 2 electron goes to Fe2 plus. Okay. So if it is like 5 millimolar, then this is also 5 millimolar. Or so then your activity of the Fe2 plus equal to some coefficient into 5. This is your activity. So that you can we are considering. this activity. So like this way also we can measure the potential of the E cell. E cell means during the reaction that I already mentioned, that one we can measure. And if the activity become 1, if the activity product is 1 and reactant also 1, so then this part becomes the 0, right? Then your E cell equals to become E0, means the formal cell, formal potential. But that is very ideal, generally not happen. This is very ideal case. So formal potential nothing, but when the activity of the concentration, I mean, when you are using all the the concentration means this part, activity part become 1, and your concentration activity part of the reactant also become 1, then actually your formal potential similar to your E cell or potential of the electrode, kind of this. Okay, so this is just some terminology that I am saying. So formal potential actually it is kind of that I say activity of the side when it become the 1. Generally in that time E cell become E formal potential. Okay. And reference electrode that I already told that its constant, its potential should be very constant. So these things generally, as I mentioned, the silver chloride one then we are using as a reference electrode. Another electrode is the standard calomel electrode. This is made by Mercury. So this is standard calomel electrode also we are using as a reference electrode. So standard calomel electrode case, its potential around 0.242 volt with respect to the hydrogen electrode. And Ag silver chloride that as I already mentioned, this is generally used for reference electrode, and its potential its potential is 0.5 volt, and with respect to hydrogen electrode, it is 0.197 volt with respect to hydrogen electrode. And in the non-aqueous means in the organic solvent. If you want to use any organic solvent, then you can use Ag plus in the acetonitrile CH3N in this solution. Ag plus. So this one can be used as a reference electrode in the non-aqueous. But in other cases, it is the aqueous solution. But leave it non-aqueous part. Our biosensor, we will always focus on the aqueous solution. Aqueous solution means we'll use some biological sample like blood, saliva, urine. So that is all of the aqueous solvent will be there. So that it means the calomel, silver chloride, or hydrogen electrode can be used as a reference electrode. Okay, students, is it okay? Fine. This kind of terminology just for your understanding and just for your reference. Okay.
Yes, sir.
Okay, so this so here is the actually hydrogen reference electrode picture that I'm not going to say. So now come to the cyclic voltammetry. So cyclic voltammetry, that is the technique. So we need some output and we want to see the structure of the output, right? So by this changing the something like peak position, or by changing their current amount, we can say how much target is present, right? Let's see. So what is the cyclic voltammetry? So cyclic voltammetry is kind of the potentiodynamic electrochemical measurement where we are measuring the current with respect to potential. So in the x-axis is the potential axis, and in the y-axis is the current axis. So we are measuring current with respect to potential. So we are scanning, that I mentioned, the anodic scan, cathodic scan, right? Just I mentioned. So this is the negative side, and here is the positive side. So right hand side is the positive side, left hand side is the negative side. So if you think about this is the like 0, and okay, let's put like this way. Sorry. Yeah, let's do like this one. Like this one 0, this one negative, and this one positive. So we are scanning anodic scan. Anodic scan means negative to positive, right? So x-axis is the potential axis. This is potential axis. Y-axis is the current axis in the cyclic voltammetry. Cyclic voltammetry short form is the CB. So now if you scan, so scan means you need any solution, like, so suppose this is your real system. So if you should have a solution, right? Not in the solid phase. So biosensor not possible in the solid phase. You should have some solution always. So because without solution, electron cannot flow. So you should have some solution. So this is your working counter reference. Okay. So suppose this is the ferric chloride solution, FeCl3. So so your iron is the +3 stage. Then it will go to Fe2 plus. So one electron will be captured. So this is called the reduction, right? And opposite stage like Fe2 to Fe3, opposite one, Fe2 to Fe3. This is the one electron release, Fe2 to Fe3. This is called the oxidation. Oxidation. And upper one is the reduction. Clear, guys? You don't think this is the so many chemistry. This is very simple reaction, right, guys? Is it clear? This reaction Fe3 plus to Fe2 plus and Fe2 plus to Fe3 plus. This is the reversible chemical reaction. Clear, student?
Yes,
So,
sir. Clear.
Yes, sir.
that's very simple reaction. Like FeCl3 ferric chloride solution, it will convert it to the FeCl2, where iron is the +2 stage. Okay, so it means it will Fe3 to Fe2 means it will gain one electron. So it means it is reduction. So this one reduction. Oxidation means it will release electron. Means Fe2 plus it will be Fe3 plus. So this is called oxidation. So Fe2 to Fe3 oxidation, Fe3 to Fe2 reduction. Say, as I said, negative to positive scan. Negative to positive is the oxidation, right? Negative to positive oxidation. So cyclic voltammetry for the Fe3, Fe2 case, you will get like this shape. So during the oxidation, so at first it will slowly, the current will be increased. The y-axis, it is the current. So current will be increase, then it will be saturated. Then it will decrease. Suppose we are scanning, so this is 0. We are scanning up to 0.5 volt. So x-axis is the potential, and potential unit is the volt. So suppose we are scanning up to 0.5 volt, and here up to minus 0.3 volt. Suppose we are scanning. So if you start from here, say here, then it will start like this. Then it will go a peak point. Then it will come in like this way. Means at the beginning, at this potential, there is no oxidation current. It means it is not possible to oxidize in this negative potential. So oxidation start only this potential. Around, suppose it is minus 0.12 volt. So in this potential, oxidation start. Then if you go more positive potential, then oxidation current also increase. See, current increase, right? The current increase. Then here is the peak current, maximum current. It is called oxidation peak potential. So this potential is the oxidation peak potential, or it is called EPA. So here, EPA, it is the anodic potential, that is EPA is the peak potential, and the current is called peak current. So correspond to this current. So this peak potential correspond to this current in the y-axis. This is called, what is this? This is called anodic peak current, and this is the anodic peak potential. Then, so see, cyclic voltammetry. Cyclic voltammetry, it is the cyclic scan. So one scan is the positive like this. Then another scan is the negative. In the same way back. So cyclic means one will go forward oxidation and backward reduction. So in the cyclic voltammetry case, oxidation plus reduction will happen simultaneously. Clear? So oxidation and reduction will happen simultaneously in the CB. So in the oxidation case, see, so it's go like this. Then from here, see the around 0. So around 0.5 volt. Then see it will start the reduction like this. Then you will get a highest reduction current here, the peak current. So this is called the reduction peak current, and this potential correspond to reduction peak potential. See, so this potential here in the picture. So this potential is the reduction peak potential, and this current corresponds to reduction peak current. Okay, so then this is the actually the cyclic voltammetry, the information we need during the biosensor measurement. Okay, I will repeat again just one more time. Guys, so make it clear, this is very simple, and every time you will use this kind of technique. Okay, hello guys, is it okay? Is it simple, clear?
Yes, sir.
Yes, sir.
Yes, sir.
Just try to understand. The first few slides I will use all the techniques. Then next few slides, then I will show you the biosensor design and how to measure by using this all the techniques. Now, more the theory, some terminology, and some technique you have to learn. Okay.
Sir, sir, how this is happening in the actual analyte solution? Like, what is going on to produce this kind of current?
Yeah. What is going on to produce this current? See here. So for the oxidation, means Fe2 plus goes to Fe3 plus, right? So for the oxidation, you should start a solution that should contain Fe2 plus. Otherwise, you will not get oxidation current. Because if you have the Fe3 plus, mean it is already oxidized. How will you can oxidize more? Fe3 to Fe4, it is kind of thermodynamically also not possible. This is not favorable process. So you should start a lower oxidation state, some electrolyte solution. Make it clear first. First point. So your solution should be lower oxidation state, contain some salt. Okay. So that contain Fe2 plus. Now, so oxidation is you are starting something. Suppose you are starting from like here in this point. This is the starting point. Okay, just remove it here. See, this is the starting point. This is the start, and this point is the final point, end. Okay, so start point already if you have Fe2 plus, now you are applying some potential, positive potential you are applying. So Fe2 plus goes to Fe3 plus electron. Because of this electron you are getting current, so that's why it is slowly increase, and at that potential you are getting maximum current, because maximum all the Fe2 plus will be converted to the Fe3 plus. And still if you apply the more potential, then because of maximum Fe2 plus convert to Fe3 plus, so your current will slowly decrease. Now clear guys why it is decrease?
Yes, sir.
So it decrease, then slowly it will go like this way, because almost all the Fe2 plus actually oxidize. Now you are going back. So here you stopped, but you are free. You can go more, but no need to go because you already got the peak current, right? Then don't go more. So you can stop it here. Around like here, suppose it is 0.5 volt. You stop. Then you go back. Means now Fe3 plus will convert to the Fe2 plus, right? So now you have maximum Fe3 plus in this point, right? Guys, you have maximum Fe3 plus, right?
Yes, sir.
Now if you apply negative back current, back means as I said, cathodic scan means negative. Now your now they will what means they will reduce, mean they will get the electron. Back scan, they will get the electron. So in this case, slowly Fe3 plus go to Fe2 plus, slowly go. Then because of this, it will current also, you will get the reduction current. See the reduction current increase. Reduction increase. Then almost uh, all the Fe3 plus they will reduce. So you will get the highest reduction current here. So this is the peak potential for the reduction. Okay, and because of almost reduce, still if you scan and if you go to cathodic scan, if you apply, then slowly it will decrease actually. So this is the whole scan. I mean the forward scan is the anodic and backward scan is the cathodic, and this is complete process is called cyclic voltammetry. See, the technique name is the voltammetry, and this diagram is called voltammogram. I think you know the spectrometry spectrogram, right? Something like this. So this is this this picture. This is called cyclic voltammogram, and technique is called voltammetry. Make it clear. Huh? This is very simple technique. So today I will teach you this kind of technique. The next class you have to apply all of this knowledge. Now this is very important. Try to understand. Guys, clear it? Otherwise, I will repeat. Just make it clear first.
Sir,
Tell me.
sir, if the oxidation is going on, then the current will be increased and we'll get a maximum positive anodic potential.
Yeah.
So then why we are using this backed? Sir?
Back. Now, back
Yes, sir.
actually, sometimes you need, as I said, we will develop different kind of biosensor. Sometimes we will develop oxidation-based biosensor. Sometimes we need reduction-based biosensor. Okay. So also, see, in your solution, sometimes you have to cycle it, oxidation reduction this way, to understand the mechanism, to understand the kinetics of your biosensor solution. Kinetics means, I will mention this one, just 1 minute. So that is very good questions actually. Who asked this one?
So it's Vibhuti, sir.
Okay, good, Vibhuti. So I think you are getting this biosensor. You are working on biosensor, right, with Kohli madam? Vibhuti?
Yes, sir. Yes, sir.
Very good.
Thank you, sir.
See, so why we need both? So it is kind of the kinetics or some information we are getting during the cyclic voltammogram. Say, if, as I mentioned, Fe3 plus goes to Fe2 plus and Fe2 plus goes to Fe3 plus, so this is kind of some reversible reaction. So if in your biosensor surface some reversible reaction going on, then you will get this kind of peak, oxidation peak and reduction peak. So you will get the very clear two peak, very close to each other. If you are getting very close to each other two peak, it means your reaction is a reversible reaction on the surface, and easily you can transfer the electron. This is very, very kinetics information you need for the development of biosensor. I will just try to remember this one, that reversible means your anodic peak and cathodic peak should be close to each other. When I will design the biosensor, that time I will again use this term. Okay. And if you are using some solution in your biosensor surface, suppose you are using a biosensor in the solution, suppose you are using glucose solution, and if you run a cyclic voltammetry, you know how you will get the cyclic voltammetry shape. So it will oxidize, then you will get oxidation peak in the glucose solution, but you will not get any reduction peak. So because glucose will be oxidized to gluconic acid, and gluconic acid further will not be reduced to glucose. That's why you will not get any reduction peak. So from this shape of the cyclic voltammogram, you can realize that your solution is reversible reaction or non-reversible, means irreversible reaction. If reversible reaction means you will get something like this. If irreversible reaction means you will get something like this. I mean this one. Means you will get oxidation, but there is no reduction peak. So reduction peak will be absent. So you will have this information. Okay, Bhuti?
So, yes,
Yeah.
sir. Yes, sir. Got it, sir.
So this kind of information we need actually. Some reversible, irreversible, if it is like this, that information we need to determine your sensor surface. So which surface is better for your biosensor? During that time, I will again repeat this term, reversible and irreversible reaction. Okay, clear, guys?
Clear.
Now another technique. This is called amperometry. So chronoamperometry. I think you know the ampero means current, right? Chronoamperometry, and coulometry means charge. Another technique, coulo means charge, chronoampero means the current. So as I mentioned, always we are going to develop some biosensor where we will apply some certain potential on. Suppose it is working, this is reference, this is counter. So we will apply some certain potential. Suppose 0.5 volt we will apply. So in this cyclic voltammogram, so potential actually varying, right? Potential are varying and your current also changing. In the chronoamperometry, we'll apply a fixed potential. So from this cyclic voltammogram, actually we will determine which potential is better for your biosensor. For that, we need cyclic voltammetry curve. So we'll decide which potential actually they are oxidized, fully oxidized. So that potential we'll decide, we'll collect from the cyclic voltammetry data. That potential we'll apply in the chronoamperometry. So before the chronoamperometry, that's why we have to run cyclic voltammetry always. Clear? So then only we'll get highest current, we'll get highest efficiency. Right? So suppose we are going to develop a biosensor that is oxidation based. Oxidation based biosensor. Oxidation based biosensor, we have to apply some oxidation potential. So see here. So in this potential, actually all the compound oxidized, right? So you can choose then this potential or more than this, not less than this. Guys, clear? Hello, students?
Yes, sir. Clear.
Yes, sir.
Yes, sir.
So if I ask you in the exam, then you have to design a biosensor, and that is oxidation based biosensor, to get highest efficiency. And I will give you this cyclic voltammogram diagram, and you have to choose a potential. Which potential will be better for that biosensor? So you have to choose more than this potential, means oxidation peak potential, more than this, not less than this. Okay. Okay. So now we are going to apply chronoamperometry. So chronoamperometry means in a fixed potential, we will get the output is the current, with respect to time. In the x-axis is the time axis, y-axis is the current. Basically, we are measuring the current in a fixed potential. In a fixed potential, we are measuring the current with respect to time. Suppose you are measuring current for 5 minutes in a biosensor for a fixed potential. So when you apply some potential, chronoamperometry shape is like this way. At the beginning, you will get very high current. Then slowly it will be going down, then it will be saturated. Then you can stop here. So why you are getting like this, I will explain. See, in the solution, as I said, it is oxidation based biosensor. Then if you have Fe2 plus, right? Reduced form you will have, lower oxidation state you will have. Then only oxidation means you can oxidize it Fe3 plus, right? So at the beginning, your Fe2 plus concentration is very, very high, right? all the compound is the reduced form. So that's why when you apply some potential, you get the highest current. Highest current you will get at the beginning, start time. At the start time, you will get the highest current. But then slowly it will go to Fe2 plus, go to Fe3 plus, and then Fe2 plus and Fe3 plus, they will be in the equilibrium, and that time this current will be constant. This current will be constant. So basically, when we will measure in our biosensor time, we will not measure the 0 second. After 0 second, maybe around 4 second or 5 second, we will measure the current, because that time the reaction will be reversible. I mean, it will be equilibrium stage. So then no change of the current. So in this time, so how much we are getting current in the y-axis, that we can measure easily. Clear, guys?
Yes, sir.
Sir, using this technique, we are getting the time for which there is current.
Yeah, respect to time, we are getting current. We are measuring current with respect to time. Suppose we are measuring a signal for 5 minutes. So from 0 to 1, 2, 3, 4, 5, like this way, we are getting the current. So at some, like in the 4-minute time, we are getting this much current in the y-axis, right? This much current we are getting here. So definitely don't consider the 0, 1, because we are getting the highest current. But after that, slowly it will be in equilibrium. So we will measure the equilibrium current.
But sir, like after some time, the current is like after 6 seconds, it is becoming 0. So if you measure after that time, then there will be no current.
No, this is something different that I am not teaching you here. It's not 0 actually. And see here, EA removed, they say. Means here actually the potential they actually removed. That's why it becomes 0. And there is no application.
Okay, sir, I didn't see it. Sorry, sir.
So don't consider this one. So just think about up to here. Okay. So this is the chronoamperometry. See, one thing here, actually one interesting thing that I will ask you. As I mentioned here, suppose in the cyclic voltammetry, so here actually it is the peak position, right? So suppose this is 0.5 volt. So this is suppose 0.3 volt, and suppose this one 0.7 volt. So if you apply 0.3 volt and then if you apply like 0.4 volt, so what will happen? So you will get higher current or lower current. Which one?
Lower current. Lower current, sir.
No, if you apply 0.3, then if you compare 0.3 and 0.4, which one will be the higher one? 0.4 or 0.4?
0.4.
0.4 will be the higher, because it is the higher one, because you are getting your oxidation happen, not reduction, right? You are applying positive potential. Oxidation will happen. See,
The downward curve, sir, the curve below the this is the x that
below one.
cathode current, na, sir. So reduction is happening, no?
Yeah, see, the below one, the reduction happened when your all the Fe2 plus converted to the Fe3 plus, and during that time the reduction will happen. So as I said, at the beginning you have only Fe2 plus, not Fe3 plus. So you will get oxidation. You will get current for the oxidation.
Sir, this reaction is reversible reaction. So far I have understand that this reaction is reversible reaction Fe3 plus to Fe2 plus or vice versa.
Right.
So if you will give this curve and ask that 0.3 or 0.4, then we will take into consideration the lower curve or the higher curve.
Right. See, that's why immediately within 0 seconds, immediately it come to the equilibrium, Fe2 plus and Fe3 plus, because it is, right?
Yes, sir.
Immediately come the equilibrium. Now you can see, if you consider the oxidation current actually here, this is the oxidation current here actually, and in this area 0.3 actually you are getting here oxidation, 0.4 you are getting oxidation here, and reduction in this case 0.3 you are getting reduction up to here, and 0.4 you are getting reduction up to here.
Yes,
But you see one thing that is very critical. but that is actually very critical. But as you asked me, that's I'm going to let you know. And very advanced level this one. Actually, when you will learn everything, that time you will understand. Actually, we have to collect the net current. 0.3 case this much oxidation, this much reduction. 0.4 volt this much oxidation, this much reduction, right?
Yes, sir.
So you have to now consider the net current. If reduction is highest, then you will get the lower current.
If
Clear?
reduction, sir,
Huh.
one minute. If reduction is highest, then lower current.
Then you will get the lower current. Okay.
So we will add the two currents and then we will see what is happening at
What's happening? Yeah. So from the cyclic voltmeter, we can consider that you are getting oxidation current or reduction current. I mean, see, this curve is because of the oxidation. So if it is because of the reduction, then what will happen? So it will come. Okay, I'll draw here. So this picture is because of the oxidation. So this is 0. So like when you are applying, if it is because of reduction, then you will get like this.
Sir, for this curve is for chronoamperometry.
This is for the chronoamperometry.
Sir,
So if it is oxidation, it will come like this. And if it is reduction, then it will come like this.
and then the curve which is shown in the slide, what is that?
That is for oxidation.
That is for oxidation.
That is for oxidation. Okay. So it means, so you have, for getting this curve, you have to apply around here or more than this, not below. So if you apply below, then which one you will get? You will get actually below one, this one. Clear?
Yes, sir. Sir, one thing I didn't get from the two curves. Sir, we are talking about equilibrium. How from the two curves, how can we tell that the equilibrium has reached or something is happening by telling the curve of cyclic voltammetry or chronoamperometry? Because it is not evident in both any of the cases.
Yeah. See, in the chronoamperometry case, so at the beginning you are using Fe2 plus, right?
Yes,
So
sir.
when you apply some potential, generally we are using very low concentration in the biosensor. We are not using very high concentration. So also in the electrochemical measurement also we are not using so high concentration. That's why when it will be oxidized immediately, it can be converted within maybe 1 second or 2 seconds. It will be converted to the Fe3 plus.
Yes, sir.
Okay, it will be converted. Now when you are applying this potential, at that potential actually all when they will be converted, but you suppose you have 5 millimolar, so slowly it will be converted from Fe2 plus to the Fe3 plus, and in your solution you already have Fe2 plus, Fe3 plus, then it also will go to Fe2 plus slowly like this, but it will not reach fully in the equilibrium until this reaction, oxidation reaction will go something like this way, this way, and until your all 5 millimolar Fe2 plus will consume to Fe3 plus, or some, no, sorry. So until this all 5 millimolar constant Fe2 plus will become to the will go to the equilibrium fully. Then it will again, all you can say that Fe2 plus all are converted to the Fe3 plus. Actually, it's not possible ideally, right? It is not possible ideally. All the Fe2 plus goes to the Fe3 plus.
Otherwise, the net current would be zero, I think.
Otherwise, the net current will be the zero, right?
Yes, sir. Because if nothing will be happening backward to forward,
Yeah.
that doesn't make any sense.
Yeah. Okay. Yeah. So if you apply some potential, if you get oxidation, then what happened? Then you will get the like this way, highest current, like around 0.5 volt you are getting here, and 0.6 volt maybe you will get the higher current. So this much current you are getting. Okay. By changing the potential, you can measure the different current. Okay. Clear?
Okay,
Yes,
sir, clear.
And another technique is the chronocoulometry. This is the last one I will teach you today. This is the last one. Then other one I will teach next class. So what is the chronocoulometry? coulometric case also, we are applying a fixed potential. Fixed potential we are applying. But what is the difference? Here we are getting charge in the y-axis, and x-axis is time, same like amperometry. So x-axis time, y-axis we are getting charge in a fixed potential, and its shape like this. Coulometry shape is like this. And why it's always changing? So you know, I think already. What is the q equals to something like this, right? Charge equals to current into time.
Time, yes, sir.
Right. As time goes on, increase. So see, it is 1, 2, like it will be increased, right? So never it will be then equilibrium. So charge always it will be increased, right? Because time increase. Maybe your current will be fixed, but because of time increase, so you will always get increase, right? So that's why chronoculogram. So this is the chronoculogram. The technique is called chronoculometry. So that's why see the charge always increase. Clear? Clear, students? Everyone?
Yes, sir.
See, now similar way it is. So if you apply like 0.2 volt, so you are getting chronoculometry like this. If you apply 0.6 volt, maybe you are getting then highest charge. So this much charge you are getting at 0.6 volt, and this much charge you are getting, suppose in the 0.3 volt. Okay, so you are getting the higher charge at this potential. So you can like this way. So suppose again if you apply like another potential, but in that case you are getting maybe somehow lower current. So which one then optimum? So where you are getting the highest charge, that is the optimum in your biosensor. So like this way, in your biosensor, you have to optimize which potential is better. So where you will get the highest signal, that is your highest signal. Also you have to consider the background also. So highest signal to background, that is your optimum applied potential. Clear, guys?
Sir, one question. What is the relationship between EP and EA? Because for EP, corresponding to EP in the chrono amperometry, voltammetry, yes. So EPA corresponds to the maximum current, and in chrono amperometry, it's EA which corresponds to a sudden spike in the current. So
Yes.
does EA and EPA crosstalk, are they same?
No. So EPA is a fixed one, but EA is the just variable one. You can choose any one. EA means it is variable. You can vary, depend. But EPA is the fixed potential. At that potential, you are getting the highest one, right? So it is fixed, but other one is variable, right? So you can apply like 0.6 volt, 0.7 volt, 0.8 volt. Then you can optimize where you are getting the highest. That one will be your optimum. So EA you can vary slowly, but EPA for a certain salt, so it is always constant. Clear?
Okay, but we cannot get a current which is more than the current at EPA, right?
Sorry, what?
Can we get a current which is more than the current corresponding to EPA for any value of EA?
No, if you consider the cyclic voltammogram, see here, so you are getting the highest current. You cannot get the more current than this EPA. You cannot.
Okay, and one thing is, in order to understand, this is almost like a hysteresis curve. So in my potential, I have my potential under my control, right? I am trying to vary my potential and seeing what is the current characteristic, so to say. And so if I go from the forward to reverse direction, from low potential to high potential, then only I can know that it is oxidized and then oxidation state, I'll have my current increasing until a particular value. And if I go back then from in the reverse direction, if I start decreasing it, then I know that reduction is taking place. So do we have a confusion really over there? What is or how is or what is the oxidation state or the reduction state, because we are knowing it, right? Because we are controlling the potential.
Yeah.
So if we increase, then only we'll have oxidation. If we decrease, then at certain stage we'll have reduction. So
Right, right, right,
right.
right. So basically, see, it will give you the more kinetic information. More kinetic information it is giving you. So here you are not getting the how much potential is +3 or +2. That you are not getting from here. Just you are getting the information of the solution. So first information you are getting, it is reversible, right? Second information you are getting, in this potential you can oxidize fully. You should always apply here or more than this, not less than this. So this kind of kinetic information you will get from the cyclic voltammogram. That's why before design, when we are designing a biosensor in a solution, always we need to run a cyclic voltammogram, and this voltammogram will give you lots of information like this area, which potential you want to apply, is this solution, which potential you should optimize. So many things you can determine from the cyclic voltammogram. That is very essential. This technique during the design of a biosensor. Okay, okay.
Yes.
Somo, you're Somo, right?
Yes, sir. Yes, sir.
Okay. What is your background? You're from chemistry.
Chemical engineering.
You're from chemical engineering. Okay, good. Nice. I think that's all for today, right? I taught you so many stuff, so many terminology, so many technique. Okay, let's go to the Wednesday again. Wednesday, I'll teach you some other new, some